Hello everyone, my name is Aravind, and in this video we are going to see about the topic undecidability, and we are going to see about the post correspondence problem, which is one of the important undecidable problems. The objectives of this video are defined below. That is, we will be seeing about language decidability, undecidable language, Turing machine halting problem, post correspondence problem, and few examples of post correspondence problem. Moving into our first topic, that is language decidability. A language is called decidable or recursive if there is a Turing machine which accepts and halts on every input string W. Every decidable language is Turing acceptable. In this image below, we have a whole set of non-Turing acceptable languages, and inside that we have Turing acceptable languages, and inside that we have the smallest subset, which is decidable language. A decidable problem P is decidable if the language L of all instances to P is decidable. For a decidable language, for each input string, the Turing machine halts either at the accept or reject states as depicted in the following diagram. In this diagram, we have an input and we have a Turing machine where there is an initial state where we will be giving the input, and it may go to two of the states. The first one, it may be a rejected state or it may be an accepted state. In either of these states, the Turing machine will halt. Moving to the next slide. Now we will be seeing whether the following problem is decidable or not. Now in our first example, given number, is it a prime number or not? For this, the solution is we have a list of prime numbers starting from 2 to the largest prime number. Now to find if the given number is prime or not, we have to divide the number m by all the numbers between 2 and the square root of m starting from 2. If any of these this method is a brute force method and it is not the most efficient way, but still we can find out whether the problem is decidable or not. If any of these numbers produce a remainder 0, that is when we divide the number m by the numbers between 2 and square root of m starting from 2, then if the remainder is 0, it is an accepted state, and if it's not, it's a reject state. So here the answer could be made by yes or no. Hence, obviously it is a decidable problem. Coming to our next example, given a regular language L and input string W, how can we check if W belongs to L? For this, we will be constructing the DFA, that is deterministic finite automata, that accepts L, and we check if W is accepted or not. Here in the diagram we have a general diagram of DFA where we give the input string W and we go into the initial state of Qi, and then in between there may be finite and or infinite, and in between the initial and the rejected or the accepted state there can be finite number of other states, and at last we can say that the given input string is rejected or accepted based on the state in which it ends. Here in the first one, the input goes into one of the rejected state. This implies W is not accepted, and if the input string ends in the final state, we can say that the language L accepts the string W. Some more decidable problems are: does DFA accept the empty language? the answer is yes or no. And the next one is L1 and L2, L1 intersection L2 equal to null for regular sets. Now we have to see a few things here. If a language L is decidable, then its complement L dash is also decidable. And the next point is, if a language is decidable, then there is an enumerator for it. Now let's get into undecidable languages. For an undecidable language, there is no Turing machine which accepts the language and makes a decision for every input string W. The Turing machine can make decision for some input string though. That is, when we give the input string to the Turing machine is supposed to halt at every alphabet. Now, for an undecidable language, there is no Turing machine which accepts the language and does not make halt for every input string. A decision problem P is called undecidable if the language L of all S instances to P is not decidable. Undecidable languages are not recursive languages, but sometimes they may be recursively enumerable languages. Next one. The most important examples of decidable problems are the halting problem of Turing machine, which we will be seeing next, the mortality problem, the mortal matrix problem, and the last is the post correspondence problem, which we will be seeing at the end of this video along with some examples. Now if we see the Turing machine halting problem, the problem is that if we have a program or an algorithm, can we say whether will it ever halt or not? Halting means that the problem on certain input will accept and halt or reject and halt, and it would never go into an infinite loop. Basically, halting means terminating. So, we can have an algorithm that will tell that the given program will halt or not. In terms of Turing machine, will it terminate on some machine with some particular input string? The answer is no. We cannot design a generalized algorithm which can appropriately say that a given program will halt or not. The only way to run the program, the only way to say whether the given program will go into a loop or not is just to simply run the program and check whether it halts or not. We can refine the halting provision in such a way also. Given a program written in some programming languages like C, C++ or Java, we have to ask, will it ever get into an infinite loop, the loop which will never end and it will keep on going, or will it always terminate, that is halt. This is an undecidable problem because we cannot have an algorithm which will tell us whether a given program will halt or not in a generalized way, that is by having specific program algorithm. In general, we can't always know, that's why we can't have a general algorithm. The best possible way is to run the program and see whether it halts or not. In this way, for many programs, we can see that it will sometimes loop and always halt. But for programs in general, the question is undecidable. To prove that the halting problem is undecidable, we use the method of proof by contradiction. At first, we will assume that such a Turing machine exists to solve this problem, and then we will show that it is contradicting itself. We will call this Turing machine as halting machine that produces yes or no in a finite amount of time. If the halting machine finishes in a finite amount of time, the output comes as yes or otherwise as no. The following is the block diagram for halting machine. Here we give an input string to the halting machine, and then in the finite amount of time the whole of the string is read and the halting machine halts on every input W and it gives the result as yes or no at each stage. Now, as in the second step, we will design an inverted machine, that is an inverted halting machine HM dash, as if H returns yes, then it will loop forever. If H returns no, then halt. The following is the block diagram of an inverted halting machine. Here we give an input string and to this halting machine, and if the result is yes during each halt, then the program goes into an infinite loop. Otherwise, the machine halts. That is, if H returns yes, then loop forever. If H returns no, then halt. Further, a machine HM2, which input itself is constructed as follows. If HM2 halts on input, loop forever. Else, halt. Here, if we see this as a whole, we have got a contradiction. Hence, the halting problem is undecidable. If you have not understood the previous explanation, I am going to explain the proof by contradiction again by using this set of code snippets. Please try to understand from this explanation. Let us assume that we can design a kind of machine called as HM and the arguments are P and I, where P is the program and I is the input. On taking input the both arguments, the machine HM will tell that the program P either halts, whether it halts or it does not halt. If we design such a program, this allows us to write another program, and let us call this program as CM of x, where x is any program which is taken as an argument here, and according to the definition of the program CM shown in the figure, the function CM calls the function HM, where we pass the arguments x, x. According to the definition of HM, it can take two arguments, that is, one is program, the other one it is the input. Now in the second program, we pass x as a program and x as an input to the function HM. We know that the program HM gives us two output. It gives us two output, either halt or else not halt, which is given here. But in case of the second program, when HM of x, x will halt loop body tells to go in loop, and when it doesn't halt, that means the loop will, and that means it is asked to return. That is, if the output of this h of x, x is equal to halt, then we will go into loop forever. Otherwise, this program is completed. That is, it is asked to return. Now we make one more situation where the program CM is again passed to CM. That is, we are going to run CM on itself. Then there will be some impossibility such that a condition which arises which is not possible. Now let us see that. It is impossible for the outer function to halt if its code, that is, there is some inner body in this loop, and it is also impossible for the outer non-halting function to halt even after its inner code is halting. So the both condition is non-halting for CM, such that we have assumed in the beginning that it would halt. So we have a contradiction. Now here if you see, we pass the same arguments to the machine CM, and here we have this code will come here, and if it's equal to halt, that means it will loop forever. And then if it does not halt, and then it will halt. It does not halt means that it will loop forever. In either way, it is going to loop forever. So both the condition is non-halting for the CM, machine or program, even we had assumed in the beginning that it would halt. So this is a contradiction, and we can say that our assumption was wrong, and this problem, that is the halting problem, is undecidable. This is how we have proved that the halting problem is undecidable. Hope you have understood this explanation. Now let's go to the next topic, that is post correspondence problem. The post correspondence problem is a popular undecidable problem that was introduced by Emil Leon Post in 1946. That's how this problem got its name. It is simpler than halting problem, and in this problem we have an popular way to demonstrate it, that is in terms of through dominoes or tiles. The aim is to arrange these tiles in such a order that the strings made by the numerator is same as the strings made by the denominator. In simple words, let's assume we have two lists, both sorry let's assume that we have two lists both containing n words, and our aim is to find out the concatenation of these two words in some sequence such that both the lists yield the same result. Now this may be hard to understand in the beginning, but if we see this example, it is very easy to understand. Let's try to understand this by taking two lists, A and B. Now the first list we have three elements, where the elements are AA, BB and ABB, and the second list is AAB and BA and B. Now for the sequence 1 2 1 3, the first list will yield, that is the first element, second element, the first element, and again the third element. Here the first element, second element, first element, and again the third element. Now if we write the elements in this order, we will get AA BB AAA BB, and the second list will also yield the same string AA BB AAA BB. So the solution to this PCP becomes 1 2 1 3. As I said before, the post correspondence problem can be it can be represented in two ways, that is in dominoes form, where each domino will have a numerator and denominator, and the next one is table form, where we have the numerator and denominator as columns and the number of domino tiles as numbers 1 2 3 4. We have 4 tiles and we have 4 rows here. Now the solution of post correspondence problem is that we have to arrange the domino tiles in such order we can repeat each tile in whatever order how many times we want, such that the string that is formed in the numerator equals, that is it is same as a string that is formed in the denominator. Now let us see an example to understand the post correspondence problem better. For that, let me use whiteboard, or we'll try to solve that here itself. Okay, let me use whiteboard to explain this. Now in the question we have got as A, that list of we got two lists which got 3 rows, and in the first one it's getting the question 1, here it's 111, and again here it's 10111, here it's 10, here it's again 10, and here it's 0. Now our first step here is to start with a tile in which both the numerator and denominator are starting with the same number. So we can either start with the first one or the second one, as both start with the same number 1. Let's go with the second tile. Let me change the colors for better understanding. This is the first step. We have chosen to start with the second tile, so A becomes 1 0 1 1 1, and B becomes 1 0. Now let's go to the second step. In the second step we need ones in the denominator to match the ones in the numerator. So we will go with the first tile, as we got ones in the denominator, that is B. This is numerator and this is denominator. So A becomes, now we are proceeding in the order 2, and now we have chosen the first tile. So now A becomes 1 0 1 1 1, and again we got 1 here, and then B becomes, we have chosen the first tile, so 1 0 1 1 1. Now again there is an extra 1 in the numerator. To match this one we will again add the first tile, that is we will again add the first tile in the sequence, so that now the string that we get in the numerator is, we copy the already existing string. Now as we are choosing the first tile, the numerator will get a 1, that is the one which is right here, and then coming to the denominator, it is B becomes, we copy the already existing string, and here if you see in the denominator we get 3 ones, this 1 2 and 3. Now if you see that in the fourth step we have an extra 1 in the denominator. To match it we will add the, as you have guessed by now, you have to add the third tile, that is the fourth step. Now A becomes, we copy the already existing string 1 0 1 1 1 1 1. If in the third tile the numerator contains 1 0 1 0, and for the denominator we copy the already existing string 1 0 1 1 1 1 1 1, then here we get 0, so 0. Now you can see that in fourth step we have got the same string in both the numerator and denominator. So our final solution is the order by which we have to arrange the tiles, that is 2 comma 1 comma 1 comma 3, and the string that we have got by the numerator and denominator is 1 0 1 1 1 1 1 1 0. This is the answer for the given first example. Now let us see the second example too. This is the first example, and then we have found that the final solution for this is 2113. Now going to the next example, we have completed it. Now let's see the solution for the second example. Again, let me use whiteboard for this to explain better. We'll delete this. Then we'll first write the question. The question is, let's make a box. We just got 3 tiles here too, and then 2 lists named A and B. We got 3 tiles. The elements are 100, 1, 0, 0, 0, 1 and 0, 0. First we have to look for tiles which have the same starting numbers. Now as we see here, we have 1 and 1 starting with 1. So in the first step we will consider using the first tile. Now A becomes 1 0 0, and then B becomes 1. Now in the step 2 we have extra 2 zeros in the numerator. To balance this, only way is to add tile 3 to the sequence. We are going to add tile 3. Now A becomes 1 0 0. Here that as there is 1, we use 1 here. Then the second string, it becomes, we enter 2 zeros here, 1 0 0. Now we get an extra 1 in the numerator. To balance this, we can either add tile 1 or tile 2. Now let's try adding tile 1 first. So A becomes, we have to tile 1, so 100 comes after the string, 1 0 0 1, and then again 1 0 0. Now B becomes, we just have to add 1 1 0 0 1. That now we see that there is an extra 1 0 0 in the numerator. To balance this, we can try adding the first tile again. Now if we add the first tile again, we copy the already existing string. It becomes 1 0 0, and the denominator it becomes 1 0 0 1, and then just 1. The 6th digit in the numerator string, which is 0, which is different from the 6th digit in the string made by the denominator, which is 1. We can try unlimited combinations like this, but none of the combination will lead us to the solution. Thus this problem does not have a solution. That is, if we use whatever combinations available in the given tiles, we will never come to a conclusion where numerator equal to denominator. This implies this PCP is does not have a solution. Now we have completed this example. There is also a theorem called as undecidability of PCP. Now this theorem states that the solution of PCP is undecidable. That is, just by seeing the tiles that is available to us, we cannot say that if there exists a solution for this PCP or not. In other words, there is no particular algorithm that determines whether any post correspondence system has a solution or not. There is also a proof for this theorem. Now we have completed seeing this example 2, in which we have concluded that there is no solution. I have shown here few problems for practice where we have the list of we have two list of elements, and then we have to find whether whether there exists a solution for this post correspondence problem. I have given 6 problems, and I have also given the answer right uh, along with the question, so that it will be, you can check whether you are doing the problems correctly or not. And another thing I forgot to say is that if the total length of all the elements in the list, if they are different, then there are chances that there does not exist a solution. For example, say in the second question we have AB, PAB, BB, AAA, and in the second list A, BA, and BAB. Here the length of all the elements in M is not equal, that is, it is actually greater than the length of elements that is present in the second list, and we can say that there is no solution for this PCP. Likewise, in the fifth question also, as the lengths are different, we have no solution. You can work out the other problems, that is first, third, fourth, and sixth, and verify if you are getting the same order, or sometimes you can also get different order, but still you can say that the solution exists for this PCPs. Now thank you for watching. Thank you.